but I got to go to Game 5 of the National League Championship Series, Braves versus the Pittsburgh Pirates, instead of doing my real analysis homework. So it was all worth it. Okay, I'm going to assume that F is not onto, on the contrary. It's actually a contrapositive proof, so we can quibble about that later. If that's true, then the number of BJs that I have are going to be less than the number of elements. You have your example at your desk. The number of the sets that you have, that you come up with, is going to be less than the number of elements. We put an absolute value sign on a set to mean the number of elements. It's also called the cardinality. That's the word we use. The cardinality means number of elements in the set. So if you let t, the absolute value of t, represent the number of elements from the set, then the number of BJs that I have, like you just did at your desk, are going to be less than the number of elements that are in T. It's going to be the way of it. There's no other way. Well, the size of S and T were assumed to be the same. So that means the number of BJs are also smaller than the cardinality of the S's, because they were the same. That means that the BJs partition S. Look at your example to see that. If you take all the union of your BJs that you came up with, you get S. So and they're all disjoint. There's nothing in one BJ that's in the other one. They're all separate from each other by definition of function. So I'm using the fact that this is a function. By the pigeonhole principle, there must be at least one of the BJs that has more than one element. I'm almost done. That means there's one of these sets that you came up with. You came up with B4, B0, B1. There's got to be one of them that has more than one element. So let's say it's BK. If BK has more than one element, then what that means is you had an F at I1 and an F at I2 that both came up to be the same K because it was in that two things were in that set. At least two things were in that set. But the I1 was not equal to I2. This is the definition of one-to-one being violated. One-to-one says that if f of x is equal to f of y, then x must equal y. But now I have an f of x equal to f of y, so that x does not equal y. So hence, I just expanded it so my reader can see I'm getting to a contradiction of being one-to-one, which was my assumption. This violates the definition of being one-to-one. So in Andrew Weil's proof, he was doing kind of the same thing. He was saying he was breaking up and partitioning sets and trying to come up with violations. If you go and think back to what he was saying, oh, this thing over here, I'm going to break it up and show that there's an equal number of packets. That's exactly the kind of argument he was using. Combinatorics is a powerful tool inside other disciplines. That was number theory. Our assumption was that it was not onto was incorrect, and it must be onto. Now I'm going to ask you to walk through step by step, and you can build examples on the side so you can understand what's going on. Take something that, like, I didn't do this on purpose. I gave you something that was not onto, so you could actually see something, but you could do the same thing. Take something that's definitely not one-to-one and start playing with it and seeing why something could go wrong. And it'll help you walk through these steps.